Emco PC turn 55 with aluminum standoffs for the Elegoo Neptune 3. Oh my god, what is this? A crossover episode? You bet your ass it is. So I bought these 18 millimeter long M4 aluminum standoffs. I also have some silicone ones upstairs, but I double checked the table height and I'm dumb. I needed 15. So, figure I have a lathe. Why not just cut them down myself? According to Elegoo, to print ABS for long periods of time, ABS, ASA, they okay. Sorry, let me back up. When you're printing ABS and ASA, you really need high bed temperatures of 100-ish or so degrees. The downside to that is that the standoffs that they use from the factory are also ABS. So what happens? The standoffs reach their glass transition temperature and they start to melt. In comes my solution, aluminum standoffs. Others have done the silicone thing, so I bought a couple of those just to try. But Elegoo recommends, if you're doing this, to only use 4 of them. I'm sure that there's something because of the additional heat transfer between the aluminum and the bottom base plate and things like that. So they said, please only use 4 if you're going to do this mod. I'll do 4. I have enough to make. Well, I've got 20 standoffs because you really need 11 for the total table, and they come in packages of 10. So, in order to circumvent the lack of the additional standoff, I bought 2 bags, which gives me a little bit of room to play with. So that being said, I'm going to make a little program just to face down using Mr. Turning Tool here. Face down 3 millimeter from each of these standoffs. I have a little drill bit that I'm just using the ground portion of shank as a stop. So I should be able to get consistency in my stick out and not have to continually measure each part. So I'm going to write a little program, and I'll set the tool up and show you guys how it's done in the subtractive manufacturing world as opposed to the additive manufacturing world. And if you're familiar with how subtractive manufacturing works, then this is not going to be new to you. So I've got the software powered up already. I'm just going to home out the machine. Similarities abound. So from here, I can jog the machine in any direction. Nice thing about CNC machines versus 3D printers is the fact that you don't have to move them in incremental steps. Basically put, in this scenario, what I have to do is I have to come in, I have to make sure that the diameter is set on the tip of the tool and also the front of the piece. The front of the piece, the diameter, gives me a triangulated 0 point for this particular tool. One thing I didn't do is recall the tool. So I'm going to back it away a little bit. Recall the tool to make sure that the turret doesn't flub out on me. So back this out. Get it to a safe spot. Nothing's going to hit. MDI. Here I'll go T4, M6, and then G43 calls up the tool offset, which should all work on one line. Okay, so it didn't have to spin anywhere, so that means that it was already stored in memory. But it's always good to be safe, especially in this world, because subtractive manufacturing, it crashes a lot more than additive. I mean, you guys may have whacked your nozzle here and there, but a machine like this crashing is never a fun time. So again, I'll bring this back in. Now I can go to MDI. I should be able to go MDI. Say G0 X of, there's 6 millimeters, so I could just say X of 0.24. Let's see where this is going to go. And there we are. So back to jog here. Bring the tool in. So I'll slow down the jog feed a little bit. That way it makes it easier to fine tune where I'm going to go. It's really the point, but the diameter seems to be set already. But if I were to have to set this diameter, what I would do is I would take a skim cut on here. I would measure this diameter inside of the tool table. This is where I could do a touch off tool X, tell it the diameter that I'm working on, and it would set whatever tool I have set here, the offset value for that particular diameter. And then when I touch off on the face of the part, I do a touch off tool Z. I choose, again, the tool that I'm going to be setting, and it'll give me a Z value of where the tool is against the face of the part in relation to where the 0 point was found using this little rod here and a switch inside. This is actually set up for double homing, which will trigger a limit switch inside of here, a little micro switch like this. But then also there is an inductive sensor tied to the lead screw. I don't know if these are lead screw or ball screw. I think they're actually small ball screw. It's hard to see. I think they are ball screw, but they are very small, like 8 millimeter. And they're very hard to find online, I'll tell you that. But anyway, there's an inductive sensor on the back that has a 1 pulse per revolution tick on it, and every time it passes that tick, it triggers the inductive sensor. So this will rough home against a limit switch and then fine feed into finding where the inductive sensor is at, and then set that as a 0 point. I do have a video on that. So in this case, I'm just going to bring this up. I won't do it on camera only because it's hard to do without a free hand, because I need to kind of spin the chuck a little bit to see if I can get some, just a little, you want to get a little bit of a fine scratch on the face of the piece. So let me just pause this real quick and I'll be back. Okay, so I came in, I just moved the chuck by hand and just brought the tool in until it touched the face of the piece. You can see a little bit of material lifting off of it. And then here, go to my tool table, make sure number 4 is selected because that's my tool number, touch off Z. And then we're going to set this to, right now we'll set this to 0.1181 because machine's running in inch mode, and that is the decimal equivalent of 3 millimeters in inch. So I'll set that, and it gives me this value of minus 3.5789. I'll go back. I'll see right here that my absolute number for my Z is 0.1181. So from here, I just want to bring it down to 0, and I want to take a cut. But what you want to do in this situation is you want to take it in small passes, just like you would layer height on a 3D printer. It's not as small, but you get a feel for it after a while. Like this machine, I can't really take too much of a cut. It's not a big machine, so I'm not going to kill it. But you want to I'll take maybe half a millimeter, 20 thousandths, something like that, per shot to get down to that 0 point. And then that should be all I need to get the part sized up, and then I'll run the other couple of pieces, and hopefully they're consistent enough that they'll work. So considering the fact that the original standoffs are injection molded ABS, there's going to be variations. So if these vary within a thou or so, a thousandth of an inch or so, 0.025 millimeter, that'll be good enough. So let me get this programmed and I'll be right back. So a real important part to CNC programming is you have to know what your code is doing. As opposed to 3D printers, you just kind of load it and go. Most people don't even pay attention to what's going on. But in this case, you have to know what all of this stuff does, because this is a much more destructive process if things don't go your way. Best way to put it. I've got my program written. The nice thing about Linux CNC is that it gives you a little bit of a sample of what it's going to do. It gives you a small graphic view of what the program will look like. And then it's basically just taking a couple of facing passes at 5 thousandths per revolution. So as the x-axis advances upward to the center of the piece, every time the spindle turns 1 revolution, the x-axis will move 5 thousandths per inch as the feed. And then at the end, it comes in and just does a little taper move here to kind of cut the front, and then it goes back to its 0 position. On CNC machines, primarily they're programmed in inches per minute or millimeters per minute, or in this case, it's being programmed in inches per revolution, or you could do millimeters per revolution. So every time the spindle turns 1 revolution, it advances this much, which makes it adaptive to the spindle speed that you're running at. I did test run this program already. I've been bringing my spindle speed up because 1,000 is just way too slow for this process. I could do it here. I could override that back to 100, or I can just go to Program, Edit, and then I can make a change to my program. Just make that 2. Here I'll save, hit the back button, and we're back to here. Program shows 2,000 RPM. I've got the rapids turned up a little bit, not 100%, but high enough. If I wanted to step into my program, this button here will single step into the program. So line by line by line, every time I press this, it's going to advance forward. But again, in this case, I've already proven this program. So I can just hit start and just let it rip. And that's all there is to it. So now with the back of the drill, I can use that against the face of the chuck to work as a workpiece stop, push my next piece in up against the workpiece stop, and then I can have a repeatable measurement. So for any of you 3D printing buffs, if you're eager to find out more about this kind of stuff, let me know in the comments. And if you are following the channel primarily for this stuff, here you go. This is probably the first production part that I've made so far. I'll spare you the pain of putting the platform on, but this actually didn't do so bad, considering the fact that I'm only using 6 of them. Elegoo recommended using 4, but I figured I'd put 2 in the middle just in case there's a crowning kind of issue. But it looks pretty good so far. I ran the gantry squaring, and the gantry squaring seemed to square up a little bit quicker than previous attempts. I'm running auto bed level now. The last time I checked, the bed was kind of cattywampus this way a little bit. I think that might have to do with my linear trucks. I put new ones on made out of PETG, and I don't know if they came out as straight as the PLA ones. So I might have to make some adjustments there, but all right, just finishing up bed level now so I can go and look at my results and see how that's going to do. I also have the silicone spacers, but I got 18 millimeter. I needed 15, so I might swap those out for 16 millimeter in the near future. Looking at pricing on Amazon right now, we want a little bit of a squish, but I don't want to have to really crank down on these things. But you want a little squish to kind of counteract the forces of the screw. That way the screws don't just back themselves out automatically. So there's my grid. It's what I expected. Like I said, it is shifted a little bit in one direction since I put the new Y-axis truck adapters on. So I'm going to do a little bit of investigating on that and see what I could do to make that better. But that may lead to a potential where using a couple of aluminum spacers will work in one situation and then fine adjust everything else with the silicone ones. The one issue that we run into is that the back edge here, it's got that wiring harness that gets sandwiched between the table, and you don't want to remove that or replace that or anything like that. You need that to keep the wiring secure. So I might do, like I said, do like this point as sort of a pivot, and then have the rest of them silicone, or at least a couple corners of silicone, whatever, and then I can dial in the rest. 0.1 millimeter is 4/1000 of an inch, and the machine is barely capable of that as far as accuracy is concerned. So I'm not too concerned about a 0.1 drift, but being that from where it tears in the center to the back edge here and here is 0.5 millimeter, which is 20/1000, that's quite a bit. But it does taper up from 20 down to almost 10, like 9 or 8. So there's a good shift there, 0.31 millimeter. So it's like 12 or 13 thousandths of an inch. And then over on this side, you got a whole 0.5. I mean, there's a lot there. So the issue is that, and I've been saying this from the beginning, is that the issue probably isn't so much the top bed itself, but a product of the fact that the top bed and the bottom bed are both stamped. And because of that stamping pressure coming down from the top, it has a tendency to belly the product, because it's doing basically a brute force operation around the edges, which is going to send the material in one direction or the other. So that could be part of the reason why it's so cattywampus in one corner on everybody's machine. The silicone spacers are good for dialing that out, because now you have control over the amount of squish that you get in each position. And then coupled on top of that is the fact that we've got this magnetic table surface, which has its own thickness, it has its own manufacturing tolerance, and it's kind of almost like rubber. So there are a lot of variables that play into the fact that the tables are not perfectly flat. I've put my feelers out to a couple of friends of mine to see if they had any cast jig plate, because cast jig plate would be the best way to go in this type of scenario, because there's no real grain structure to casting. It's just a bunch of granules that are melted together. And in that situation, they would all grow in different directions, so the warpage wouldn't be as bad, because they don't have the one direction that's picking up that warpage. They would just kind of expand together. I was actually thinking of figuring out a way to do some sort of kinematic floating bed, but it's impossible on a slinger. So that about wraps up this crossover episode. I hope you're enjoying the content. If you haven't yet, and you do like the content, please like and subscribe. It helps a lot with the channel, and it helps me get taken a little bit more seriously with some of these companies. Thank you for watching, and we will see you soon.